In this video, we're going to explore the second largest topic in calculus, and that topic is integrals. So here's the agenda for today. We'll start by exploring what the integral actually is and what it's used for. We will then cover the key techniques that you'll need to know for solving integrals. And while we're at it, I'll also address one of the major issues that comes up with the formula sheet, so stick around for that. Let's get into it. Integration and differentiation are two sides to the same coin. In fact, one of the alternative names for integration is anti-differentiation. So if you haven't studied differentiation yet, do that first. I've left a link in the description for you. The purpose of integration is to reverse the process of differentiation. For example, suppose you started with the function f of x equals x squared. Its derivative would be 2x. If you want to go back to f of x, then integration is required. Integration is done by using a table of known integrals, much like differentiation is. The left-hand side of the table represents the function that you start with. The little squiggle to the left and the dot dx simply represents taking the integral of that function. The right-hand side of the table represents the result after integration. For example, this table tells us that the integral of x to the power of n is just 1 divided by n plus 1 multiplied by x to the power of n plus 1. But there's also this plus c term in there. Let's take a look at why. Let's suppose we have two functions, f of x equals x squared plus 3 and g of x equals x squared plus 300. If we want to take the derivative of f of x using the table of known derivatives, then the derivative is going to be f dash of x equals 2x. If we then want to take the derivative of g of x, then we'll also find that its derivative is 2x. Even though we have two different functions, they have the same derivative. Now, let's try integration. We said earlier that the integral of a function reverses the process of differentiation. So the integral of 2x should take us back to either f of x or g of x. Currently, it doesn't look like 2x actually fits on that table. The goal here is going to be to manipulate that equation until it fits on the table, and we do that by using the two key properties of the integral. Firstly, if your function has a coefficient, then you can take that coefficient on the outside of the integral. And lastly, if you're trying to find the integral of an addition or subtraction of two functions, then you can instead find the integral of each function individually and then just sum the results up. Using the first property, I can take that coefficient of 2 outside of the integral. And I'll also raise x to the power of 1. This doesn't really do anything to the function, but it does make it a lot easier to figure out where it fits on the table. So we have an integral of x, and that x value is raised to some power. This fits the second entry on the table. So all we have to do is increment that power by 1, and then divide through by that new power. And so, after some simplification, we arrive at our answer, x squared plus c. Don't forget, at the start we took out that coefficient of 2. Just because we took it out doesn't mean we don't have to put it back in at the end. Notice how I didn't multiply the c term by 2? That's because the c term is a little bit special. It's there to simply represent a constant. It's there because, just by looking at the derivative, there's no way of figuring out what the constant of the original function must have been, or if it even had a constant at all. Even though f of x and g of x are two separate functions, they both have the same derivative. So if you only look at the derivative, then there's no way of knowing what that constant must have been. The plus c term is the constant of integration. It's simply there to tell you all the possible functions that f of x could have been. That's why it doesn't really mean anything to say 2c rather than just c. They would both serve the same purpose, and that purpose is just to say there could have been a constant in this result. That's why the integral is sometimes referred to as the indefinite integral, because it's not a perfect reversal of differentiation. Let's try to find the integral of a more complicated example. Firstly, we can use the second property to split that integral up into two individual integrals rather than one big one. And then lastly, we can use the first property to take those coefficients outside of the integral. Once we've done that, we're in a position where we can just match its spot on the table and then substitute accordingly. All we need to do from here is simplify the expression and then combine the plus c term. Again, there's no need to leave a coefficient on the plus c, it just needs to be there to represent a constant. Your formula sheet actually comes with a table of known integrals, but there's a problem with it. It doesn't cover all the possibilities that can come up in a tech-free exam. Now, don't get me wrong, there's a lot of things that the formula sheet doesn't cover, but this particular example is a little bit deceptive. That's why I wanted to cover it. The major issue here is the hyperbola. Let's find out why. So this is a 1-mark question that came from the 2022 tech-free exam. No calculator to help us out. Already we have a problem. Unlike the other integrals, we don't know how to handle that coefficient on the x. Now, we could take that coefficient outside of the integral, but we're still in a position where there's a constant on the denominator, and we don't know how to handle that. There's actually no way to rearrange that hyperbola to get it to match the table of integrals. For now, I'll show you a shortcut. The table of integrals should look more like what I've got on the right hand side. The coefficient on the x is going to be a division of the entire result, and the linear term of the hyperbola is just going to be inside of the logarithm. Let's apply that to this question. Firstly, we're going to take out that coefficient of 3 outside of the integral so that it looks like our table of integrals. Then from here, it's just plug and play. The linear term 2x minus 3 will go inside of the logarithm, and we're going to divide that entire result by 2, since 2 was the coefficient of the x. Then to finish off, we're going to bring that 3 back into the equation. Remember, this was a tech-free exam. This is a formula that you have to memorize. There's actually a lot of different ways to break the table of integrals. This is just the only way that I've seen it break in a tech-free exam. It breaks all the time in tech-active exams, but that's because you have the CAS to help you out. The definite integral is slightly different to the indefinite integral. And you can always recognize if you have a definite integral because it adds 2 new terms to the integral. These are called the terminals of the integral. The definite integral is actually a calculation, and it's found by finding capital F of b minus capital F of a, where a and b come from the terminals of the integral, and capital F of x is just the integral of f of x. Let's try an example. We're told to find the integral from 1 to 4 of f of x. First things first, we need to find capital F of x, and we do that by using our table of integrals. The first problem is that it doesn't look like the function belongs on the table of integrals. We have to do a bit of rearranging. Firstly, let's recall that the square root of a function can be rewritten in indices form. And then lastly, we can remove the fraction by just rewriting it as a negative indice. And suddenly, we have a match on the table of integrals. And then lastly, we're just going to sub in the terminals of the integral. This gives us f of 4 minus f of 1. And after a bit of simplification, we're left with a single value. Furthermore, you'll also notice that the plus c term disappeared. This will always be the case for any definite integral, so it's often ignored during the working out. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it'll send you to my website.